to the part 2. Number 5. Melting and boiling points. Melting and boiling point of elements tell us something how strong the atoms or molecules in them are bound together. A. Variation in a period. Across the short periods, the melting and the boiling points of elements increase with the number of valence electron up to group 4A and then decrease up to the noble gases. The melting points of group 1A elements are low because each atom in them provides only one electron to form a bond with other atom. Melting points of group 2A elements are considerably higher than those of group 1A elements because each atom in them provides two binding electrons. Variation of melting points with the atomic number. Since carbon has the maximum number of binding electrons, thus it has a very high melting point in diamond in which each carbon is bound to 4 carbon atoms. In general, the elements which exist as giant covalent structures has very high melting points, such as given in the figure 1.5. An important change occurs when we move from group 4A to group 5A, 6A and 7A as the lighter elements of these groups exist as small covalent molecules rather than as three-dimensional lattices. For instance, nitrogen, oxygen and fluorine exist as individual molecules which have very weak intermolecular forces between them. Consequently, their melting and the boiling points are extremely low. B. Variation in a group. The melting and boiling points of 1A and 2A group elements decrease from top to bottom due to the increase in their atomic sizes. The binding forces present between large size atoms are relatively weaker as compared to those between smaller atoms, figure 1.6. For elements of group 7A which exist in the form of molecules, the melting and the boiling point increase down the group, shown in the figure 1.7. This is because large molecules exert strong force of attraction due to their higher polarizabilities. Melting points of group 2A elements are shown here. 6. Oxidation state. The oxidation state of an atom in a compound is defined as a charge with the sign which it would carry in the compound. In ionic compounds, it is usually the number of electrons gained or lost by the atom. As in the case of sodium chloride, the oxidation state of sodium and chlorine are +1 and -1, respectively. In covalent compounds, it is decided on the basis of the difference in the relative electronegativities. For example, strontium chlorate is a covalent compound. The oxidation state of tin plus 4 and that of chlorine is -1. The oxidation state of an element is 0 in its free state. The oxidation state of a typical element is directly or indirectly related to a group number to which the element belongs in the periodic table. The elements of group 1A to 4A have the same oxidation state as their group numbers are, just as boron, aluminium and gallium belong to group 3A. Hence, they always show the oxidation state of +3. So, for the elements of these groups, the oxidation state is same as the number of electrons present in the valence shell of the elements. However, for the elements of group 5A, the oxidation states are neither either the number of electrons present in the valence shell, which is same as the group number, or the number of vacancies available in these shells. For example, nitrogen, potassium, astatine and Sb frequently show +3 as well as +5 oxidation states. Elements of group 6A show almost similar behavior. In H2SO4, sulfur shows the oxidation state of +6, which is the number of electrons in its outermost shell, whereas its oxidation state is -2 in H2S, which is the number of vacancies in the shell. In group 7A, elements oxidation state is mostly -1, which is again the number of vacancies in their outermost shell. Group 8A elements, which are also called the zero group elements, usually show zero oxidation state because there is no vacancy in the outermost shell. Transition elements, which are shown in the B subgroups of the periodic table, also show the oxidation state equal to their group number, as it can be seen for copper 1, zinc 2, vanadium 5, chromium 6 and manganese 7. But due to the greater number of valence electrons available in the partially filled d orbitals, these elements usually show more than one oxidation states in their compounds. Number 7, electrical conductance. One of the most familiar properties of metals is their ability to conduct electricity. This property is mainly due to the presence of relatively loose electrons in the outermost shell of the element and ease of their movement in the solid lattice. The electric conductance of metals in groups 1A and 2A generally increases from top to bottom. However, the trend is not free from the individual variation in different atoms. Metals of group 1b, which are known as coinage metals, have atoms metal of group 1b, which coinage metals have extraordinary high values of electrical conductance. Non-metals, on the other hand, especially of group 4a, 6a, and 7a, show such low electrical conductance that they can be considered as non-conductors. In the series of transition metals, the values of electrical conductance vary so abruptly that no general trend can be assigned to them. Carbon in the form of diamond is non-conductor because all of its valence electrons are tetrahedrally bound and unable to move freely, while in the form of graphite, carbon is fairly good conductor because one of its 4 electrons is relatively free to move. The lower elements of group 4a, tin and lead are fairly good conductors and their values of electrical conductivity are comparable with those of their counterparts in the group 1a. 8. Hydration energy. The hydration energy is the heat absorbed or evolved when 1 mole of gaseous ion dissolve in water to give an infinitely dilute solution. For example, when 1 mole of gaseous hydrogen ions are dissolved in water, resulting in an infinitely dilute solution, a large amount of heat is liberated. H plus H2O is H3O hydronium ion and the delta H is minus 1075 kilojoule per mole. Hydration energies of few negative and positive ions are shown in the table 1.2 as you can see here, and it is evident from the table that the hydration energies highly depend upon the charge to size ratio of ions. For the given set of ions, for example of group A, charge to size ratio decreases from top to bottom in a group. The hydration energy also decreases in the same fashion. On the contrary, the hydration energy increases significantly by moving from left to right in a period as the charge to size ratio increases as found in the metal ions of the third period. Allah Hafiz.